everyone, I welcome you all in this new lecture series of partial differential equation of order 1. In this lecture series, I will discuss the linear and non-linear partial differential equation of order 1. Today, I will discuss the formation of the partial differential equation of order 1. So, linear partial differential equation. For partial differential equation, linear or non-linear, linear or non-linear. For partial differential equation, is said to be linear if the dependent variable, say dependent variable is z. So as we are discussing the partial differential equation, that means there will be a dependent variable and we can have more than two independent variables. So if the dependent variable, say your z, and its partial derivatives occurs in degree 1 and in degree 1 and are not multiplied. That means, it means a partial differential equation is said to be linear if the dependent variable, say your z, and its partial derivatives can be del z upon del x, del z upon del y, occurs in degree 1. That means they should have degree 1 and are not multiplied. That means z and del z upon del x cannot be multiplied. Such type of partial differential equation are said to be linear partial differential equation and otherwise non-linear. PD, non-linear partial differential equation. For example, in the first example, you can see that, say this is your first example. Here you can see that the partial derivatives has degree 1, so you can say that it is your linear. And in the second example, you can say that, suppose that here we have del z square and then del z upon del x whole square plus del z upon del y square is equal to, say, some xy. Now here you can see that the partial derivative has degree 2 and the dependent variable is in multiplication with your del z upon del x and del z upon del y. So here the first equation is linear and the second equation is non-linear. So these are the examples. Now let us find out the partial differential equation of some algebraic equation. So formation of partial differential equation. The first case, if suppose that your function is of the type, suppose that function is of the type f of x, y, z, a, b equal to 0. Suppose that this is the type of the problem. That means we have a function of x, y, z and some constants a and b. Now, if this is the type of the problem or question, then say this is your equation number 1 and we will differentiate this equation with respect to x. Now differentiating one partially with respect to x, we get, now the differentiation of this function with respect to x means del f upon del x. We are defining here we are doing the partial differentiation. So it means if you are differentiating with respect to x, then first of all we will have to differentiate f with respect to x, and then differentiation of x with respect to x will be 1. Then we will differentiate f with respect to y, and then we will differentiate del y upon, then we will differentiate y with respect to x. Then we will differentiate f with respect to z, and then differentiation of z with respect to x. And the differentiation with respect to a and b will be 0, so this is equal to 0. Now, if your z is a function of x and y, suppose that your z is function of independent variable x and y, then your x and y are independent variable and z is depending on x and y. So as x and y are independent to each other, so this derivative will be 0. So this is your equation number 2, del f upon del z, and del z upon del x is denoted by p. So this is your equation number 2, where my p is this del z upon del x. And similarly, on partial differentiation with respect to y gives, now if we differentiate with respect to y, then our x will be replaced by y, and here we will get del z upon del y, and del z upon del y is q, so this is equal to 0. So this is equation number 3. Now on eliminating a and b, from equation number 1, 2 and 3, we will get the partial differential equation. So on eliminating a and b from equation 1, 2 and 3, we get partial differential equation. So this is the method of finding the partial differential equation, or you can say the formulation of the PD. And this is when we have the constants a and b. So this is your first case when we have the constants. So you can also say it as elimination of constants. In this first case, we will eliminate our constants. So let us solve problems related to this method. The first one, or formulate partial differential equation for the first question, z equal to ax plus by plus some function of a and b, say a square plus b square. Second problem is x minus h whole square, y minus k square plus z square equal to lambda square, where your lambda is the radius of the circle or radius of the sphere. Then third question, and we will have to eliminate h and k. The third question is z equal to x square plus a into y square plus b, and the fourth problem is 2z equal to ax plus y whole square plus b. Now formulate partial differential equation for these problems. In all these four problems, we will have to eliminate our constants, say a and b in the problem 1, h and k in the problem number 2, and a and b in the problem number 3 and 4. So solution. The first part, z equal to ax plus by plus a square b square. So this is equation number 1. Now we have to eliminate a and b by partial differentiation of z with respect to x and y. So the partial differentiation of this z with respect to x will be del z upon del x, and now the partial differentiation of this equation with respect to x will be your a. Partial differentiation of y with respect to x is 0, and again a square plus b square is constant, so del z upon del x is a. or you can say that A equal to del z upon del x, and del z upon del x has notation P. And if we differentiate this equation number 1 partially with respect to y, we will get the differentiation of ax will be 0, and here we will get b. So you can say that b equal to del z upon del y, and del z upon del y has notation q, so b is q. Therefore your answer is z equal to ax, that means px plus qy plus some function of p square plus q square. So this is your partial differential equation as it contains the partial derivatives p and q. Now the solution of the second part. This is your first part. Then let us solve the second part. In the second part we have x minus h whole square plus y minus k whole square plus z square equal to some lambda square. Here lambda is your radius, so it will vary, and now h and k are constants. So here we will have to eliminate this h and k. So on differentiating, say this is your equation number 1 partially with respect to x, we get, and the partial differentiation of this one with respect to x will be, now the differentiation of this one with respect to x will be your 2y minus k, and then partial differentiation of y with respect to x will be del y by del x, and that will be your 0 because x and y are independent to each other. So as we are differentiating partially with respect to x, so this term will be constant because x and y are independent to each other. In case of function of two variable, your x and y will be independent to each other. So on differentiation partially with respect to x, this will be your constant, so its differentiation is 0. Then the partial differentiation of z square will be 2z, and then partial differentiation of z with respect to x is del z upon del x, and this is equal to 0, and del z upon del x is p, so this will be your x minus h equal to minus zp. Again differentiating 1 partially with respect to y, we get, so if you differentiate this equation with respect to y, we will get 2y minus k plus 2z into del z upon del y equal to 0. So from here we will get y minus k equal to minus z times q. So say this is equation number 2, and that is your 3. Now from 2 we have the value of x minus h. From equation 3 we have the value of y minus k. Let us put equation number 2 and equation number 3 in equation number 1. Thus from 1, 2 and 3 we have, let us put the value of x minus h. So this will be your z square p square, then y minus k whole square will be z square q square plus z square equal to lambda square, and this is your answer. We can also write it as z square p square plus q square plus 1 equal to lambda square. So this is your answer. Third question is very easy, so I am not solving it. Let us solve the fourth problem. So fourth problem, 2z equal to ax plus y whole square plus p. So its partial differentiation with respect to x will be 2 times del z upon del x equal to, the partial differentiation of this will be your 2ax plus y, and then partial differentiation of x plus y will be your a, and here we will get 0. So then the partial differentiation of x will be your a. So that means p equal to a times ax plus y. So this is your equation number 1. So say this is your equation number 1 and it is your equation number 2. Again differentiating 1 partially with respect to y, we get, now the partial differentiation of this one with respect to y will be your 2 del z upon del y equal to 2 times ax plus y, and then the partial differentiation of this with respect to y will be your 1. So from here, the value of ax plus y is equal to 2 times, or you can say that your q equal to, this will be your 2 and 2 cancel, we will get ax plus y. Now from equation number 2 and 3, let us divide 2 by 3, thus by 2 and 3 we get P upon Q equal to A. So P upon Q is equal to A. So we have the value of A as P upon Q. Now let us put the value of A in equation number 3. We can also put the value of A in this equation, as we have to find out the partial differential equation. By eliminating A and B, we have already eliminated B by differentiating one partially with respect to x or y. Now to eliminate A, let us put the value of A in equation number 3. Hence by 3, we will not put this value in equation number 1, otherwise we will have a constant B. So let us put this value in equation number 3. Hence by 3, your Q will be Ax, that means P upon Q x plus y. So that means your Q square is equal to Px plus Qy. So this will be your answer. So this is your partial differential equation. Okay, now in the next case, we will formulate partial differential equation by eliminating the function. So second case, formulation of PD by eliminating functions. So let us formulate partial differential equation by eliminating the function. Consider the function. Let us consider a function f of phi of u v equal to 0. That means we have a function of u and v. And what is u? Where u and v are functions of x, y and z. That means basically we have a function of x plus y plus z, x, y and z at u and at v. So if the type of function is some function of x, y and z, comma another function of x, y and z, then we will try to eliminate this function phi. So to eliminate this function phi, let us differentiate one partially with respect to x and partially with respect to y. So differentiating one partially with respect to x. Now if you differentiate this equation partially with respect to x, then now we cannot differentiate this one directly with respect to x because it is a function of u and v. So we will have to differentiate one first with respect to u. So this will be your del phi upon del u and then del u upon del x. Then we will have del phi upon del v, okay, del phi upon del u, and then we will have del u upon del x. Now, but u is some function of, say u is some function of x, y and z. Now as u is a function of x and y and z, so this bracket, now use the chain rule. Now use the chain rule of the partial differentiation. Here as we are differentiating partially with respect to x, we will get del phi upon del u, but your del u upon del x will be, as we are differentiating this function with respect to x, so this will be your del u upon del x will be del u. Now we will differentiate first with respect to x, and then differentiation of x with respect to x means del x upon del x. Then we will differentiate u with respect to y, and then differentiation of y with respect to x. Now as x and y are independent to each other, here you can see that all x, y and z are independent to each other. So del u upon del x, then del x upon del x, then next term will be del u upon del y and del y upon del x. That will be your 0. And the third term will be del u upon del z and del z upon del x, and del z upon del x is p. So this is your first term. Here your z is a function of x, y, not They are not independent to each other, but z is depending on x and y. So this is your first term, and in the next term we will differentiate phi with respect to v, and then the differentiation of v with respect to x, and this will be your del v upon del x and del x upon del x. Then we will have del v upon del y, and del y upon del x will be 0, and the third term is del v upon del z, and del z upon del x is equal to 0. So that means, so we can write it as del phi upon del u. Now del u upon del x, this is your del z upon del x is p, so we can write it p del u upon del z. Then we will have del phi upon del v, and then here we will have del v upon del x plus q plus p times del v upon del z is equal to 0. So from this equation we will get the ratio del phi upon del u upon del phi upon del v, and this is equal to del v upon del x plus p times del v upon del z divided by del v upon del x plus p times del v upon del z. So this is the equation number 1. Say it is equation number 2. Now again we will differentiate equation number 1 partially with respect to x. So similarly, on differentiating one partially with respect to y, we will get y in place of x. So just replace your x by y, first point, and then at this place, in place of del z upon del x, we will get del z upon del y, and del z upon del y is q. So in place of p, you will get q, and you can replace your x by y. So similarly, on differentiating one partially with respect to y, we get, so the left hand side will be same, and in the right hand side just replace your x by y and p by q. So we will get this term. So here you will get del upon del y and then q del upon del z. Now as you can see that equation number 2 and 3 have same left hand side, so their right hand side will be equal to each other. So by 2 and 3 we will get del upon del x plus p times del upon del x plus p times del upon del z divided by del upon del x plus p times del upon del z is equal to del upon del y plus q times del upon del z divided by del upon del y plus q times del upon del z. So this is your result using the equation number 2 and 3. Now let us cross multiply these two equations. So we will get del upon del x. Let us multiply this term by this term. So we will get del upon del x into del upon del y. Then we will get q times del upon del x into del upon del z. Then we will get p times del upon del z into del upon del y. Then we will get pq del upon del z into del upon del z, and in the right hand side we will have del upon del x into del upon del y plus q times del upon del z into del upon del x plus p times del upon del z into del upon del y, then pq del upon del z into del upon del z. So you can see that this term is cancelled, and now let us take p and q common. So if we take terms of v as common, then we will get here del upon del z into del u upon del y. This is your b. So this will be your del u upon del z into del u upon del y minus this term del u upon del z into del b upon del y. Then we will have plus q into del b upon del x, del u upon del z minus del b upon del z into del u upon del x. Then equal to, we will have this term del u upon del x into del b upon del y minus del b upon del x into del u upon del y. So if you write this term as capital P, then therefore your some capital P into small p plus some another function capital Q into small q equal to, say this is your equal to capital R, where the first bracket is our capital P. I have assumed this one as capital P. So if this is your P, then you know that with the help of the Jacobian, this term can be written as UB upon del YZ. This is your capital P. That means it is the Jacobian of where this is your del u upon del y into del u upon del z and del u upon del y into del u upon del z. So you can see that it is equal to del u upon del y into del u upon del z minus del u upon del y into del u upon del z. So this was your P. You can see that this is your del u upon del y into del u upon del z minus del u upon del z into del u upon del y. So this is your P, and similarly, and we can write Q as del of uv upon del zx, and then your R is del of uv with respect to del of xy. So this is your partial differential equation, and where P is Jacobian of uv with respect to yz, Q is Jacobian of uv with respect to zx, and capital R is Jacobian of uv with respect to x and y. So this is your partial differential equation, and we have obtained this partial differential equation by eliminating the function. And this is known as, this is a very important type of partial differential equation, and later on we will solve this type of partial differential equation. That means we will take the partial differential equation and we will try to solve this differential equation, and it is known as Lagrange's form of partial differential equation. So now let us formulate some questions. Second problem, formulate PD for the A part. Say there is some function of x plus y plus z and x square plus y square minus z square equal to 0. Second part, x plus y plus z is some another function of x square plus y square plus z square. In the third part, we have z equal to some function of y upon x. In the fourth part, z equal to e to the power x plus by into f of ax minus by. In the fifth part, we have z equal to f of x plus iy into plus some another function of x minus iy, where your I square is minus 1. And then the sixth part is z equal to y into f of x plus x into g of y. And we can have the next part, f x minus a upon z minus c, and then y minus b upon z minus c equal to 0. So these are the questions. Now let us solve the first part. Solution of the first part. So here your phi is this function, and if u equal to x plus y plus z and v equal to x square plus y square minus z square, then your phi u comma v is equal to 0. Now let us differentiate this equation 1, differentiating 1 partially with respect to x. So if we differentiate this equation partially with respect to x, we will get del phi upon del u, and the partial differentiation of u with respect to x will be del u upon del x, and then del u upon del z into del z upon del x. We are solving in a similar fashion as we have derived the formula, and then we will have del phi upon del v, and then del v upon del x, and then del v upon del z into del z upon del x. This will be your 0. So here you can see that this is your del phi upon del u and del u upon del x. Now the partial differentiation of u with respect to x is 1, and del u upon del z, it is again 1, and del z upon del x is p. So this is 1 plus p into this function plus del phi upon del v. Then here we will have del v upon del x as 2x. Then from here we will get del v upon del z as minus 2z into del z upon del x is p. So this is equal to 0. Therefore, del phi upon del u upon del phi upon del v is equal to, this is equal to, and this is equal to 2 times zp minus x divided by 1 plus p. So this is equation number 2. Again, differentiating 1 partially with respect to y. Now if we differentiate 1 partially with respect to y, we will get del phi upon del u, and then the differentiation of u with respect to y, and that will be your del u upon del y into plus del u upon del z into del z upon del y. Then we will have del phi upon del v, and in the bracket again we will have del v upon del y plus del v upon del z into del z upon del y. This is equal to 0. So as our u was x plus y plus z, so this del u upon del y will be 1, and again del u upon del z will be 1, so this is your 1 plus q, and here we will have del v upon del v. Now del v upon del y as v equal to x square plus y square minus z square, so del v upon del y will be 2y. Then this del v upon del z will be, this del v upon del z is equal to minus 2z, and then here we will have q. So from here del phi upon del u, del phi upon del y divided by del phi upon del v is equal to your zq minus y divided by 1 plus q. That means you can see that our x is replaced by y, and in place of p we are getting q. So by 2 and 3, your solution will be equal to your right hand side. So your zp minus x upon 1 plus p is equal to zq minus y upon 1 plus q. So this is your answer, and you can multiply both sides. You can cross multiply it and you can simplify it. So this is the answer of the part 1. And in the second part, now let us solve the second part. So B. Here we have x plus y plus z equal to some function of x square plus y square plus z square. So let us differentiate this equation partially with respect to x. So differentiating, say this is equation number 1 partially with respect to x. So differentiation of this one with respect to x will be your 1, and then del z upon del x will be your p. Now the differentiation of this function will be, say, f dash, and then the partial differentiation of this bracket with respect to x will be 2 times x, and the differentiation of y square will be 0, and differentiation of z square will be 2z, and differentiation of z will be del z upon del x, which is your p. So from here your f dash is 1 plus p upon 2 times x plus zp. Again, Let us differentiate 1 partially with respect to y. And similarly, differentiating 1 partially with respect to y, we get, as you can see that x and y are symmetrical to each other, so just replace your x by y and p by q. So similarly, on differentiating partially with respect to q with respect to y, we will get 1 plus q divided by 2y plus z into q. Therefore, your answer will be 1 plus p upon x plus zp is equal to 1 plus q upon y plus zq. So this is your answer, and you can cross multiply both sides. So you can see that it is similar to the answer of the first part. Okay, in the third part is, I think, quite easy, and you can solve it very easily. Here z is some function of y upon x, so your del z upon del x will be, the partial differentiation of the function will be your f dash, and then partial differentiation of this bracket with respect to x will be minus y upon x square, because y will be constant and the partial differentiation of 1 upon x is minus 1 upon x square. So your p equal to f dash y upon x into minus y upon x square. Similarly, differentiating y, again del z upon del y will be, now the differentiation of this function will be f dash, and the partial differentiation of this y upon x with respect to y will be your 1 by x. Let us divide this equation number 1 and 2. So this will be your del z upon del y, and this is your q. So 1 divided by 2 implies p upon q equal to minus y upon x square into 1 by x. So you can see that your p times x plus q y equal to 0. So this is your partial differential equation in the problem number 3. Similarly, you can solve the equation number 4, which is again similar to the equation number 3. Question number 4 again is similar to the question number 3, C part. G part is similar to the part A. Now let us solve the part F. I think F is different part, so I am solving this part, and rest part are similar to each other. So F, here our z equal to y some function of fx plus x some function of y. Now let us differentiate this one with respect to x. So you will get del z upon del x equal to, now y will be constant, so differentiation of x will be your f dash x, and the differentiation of x is 1, so you will get gy. So this is your equation number 1 and this is your equation number 2. Also, your del z upon del y will be the partial differentiation with respect to y. From here we will get fx, and from here we will get x g dash y. So this is your equation number 3. Now let us differentiate equation number 3 partially with respect to x. We are doing partial differentiation with respect to x to eliminate this function x. So on differentiating this equation with respect to x, we will get del 2 z upon del x del y. Here the partial differentiation of fx will be your f dash x, and the partial differentiation of x is 1, so you will get this term. Thus del 2 z upon del x del y will be f dash x plus g dash y. Now from this equation number 2, let us eliminate our f dash x, and from equation number 3, let us put the value of g dash y. Put f dash x and g dash y from 2 and 3 in equation 4. Thus we have, so on putting the value of f dash x and g dash y from 2 and 3 in equation 4, we get del 2 z upon del x del y is equal to, now your f dash x will be, del z upon del, this your f dash x will be 1 upon y, del z upon del x minus gy, and then we have g dash y, and this g dash y will be 1 by x del z upon del y minus f of x. So on taking LCM, we will get, now this is your p, so we will get p upon y, and here we will have minus gy upon y. This term is q upon x, and then here we will get minus fx upon x. Okay. So now let us take LCM. Now if we take LCM, then we will get, in this term we will get x into gy plus y into fx divided by x into y. Now let us combine these two terms. If we combine these two terms, we will get this term x gy plus y fx upon xy. Now x gy plus y fx is, x gy plus y fx is equal to z. So therefore the left hand side, del z upon del x del y is equal to p upon y plus q upon x minus, this is your z upon xy. So this is your answer.